Welcome and thanks for joining us. I'm Linda Bell, Editorial Director at SAE Media Group. I'll be your moderator for today's webcast, Getting Started with Multiphysics Simulation in the Cloud with SimScale, sponsored by SimScale. Today's webcast will last about 30 minutes, and there will be a question and answer period at the end of the presentation. You can submit a question anytime by entering it in the box at the bottom of your screen. Our presenter will answer as many questions as possible following the presentation, and those questions not answered during the live event will be addressed following the webinar. In order to view the presentation properly, please disable any pop-up blockers you might have on your browser. So now let's meet our speaker. David Heine is the co-founder and CEO of SimScale, a cloud-native simulation platform that empowers engineers to innovate faster by making high-fidelity engineering simulation truly accessible. David holds degrees in mechanical engineering, mathematics, and CSE from Georgia Tech and Technical University Munich. Now I'd like to hand the program over to David Heine. David?
Thank you so much, Linda. Really appreciate it. And I'm excited to be here today. And for the next 30 minutes, what I will talk about is, as Linda just said, is how to get started with multi-physics simulation in the cloud. And I think an important thing I want to stress right away in the beginning is, with the danger of stealing a bit the thunder of the rest of the presentation, is that with getting started, I really mean getting started. So everything I'm going to show you today, we're going to see a bit of a live demo. We're going to see a few applications you can simulate with this cloud-based tool, SimScale, that I'm going to show you. All of them you can repeat yourself via the materials we'll provide by the end of the session. So on the last slide, we will provide links to tutorials to repeat those simulations. So if any of those are relevant to your field of work, that could be interesting. It's not going to, just remain some presentation, some colorful pictures. We've all seen them, but it can be something where you can directly get your hands on and start using it yourself. But we're going to see that in a second. I will start with a quick introduction about the company, SimScale, about how our view on the world, about how we think the use of simulation will evolve over the next years. And, I think it's going to inform a lot the live demo you're going to see afterwards. And in the second half of the session, I want to go through 3 simulation examples from different physics. And we're going to get our hands dirty and actually run some simulations together in this session. But now, enough of the pre-talk. Let's directly get into it. Quickly about the company, we're about 100 people, headquartered in Munich, Germany, and over the last, almost 10 years by now, we onboarded hundreds of thousands of users, and that ran millions of simulations on SimScale already. And throughout all of this time, we're always have been on the same mission. And Linda said it already in the beginning, that that we're on a mission to empower engineers to innovate faster. And I think the important aspect is we do that by making simulation technically and economically more accessible. And I like to stress that a lot, because there's a lot of simulation vendors out there, and yet another one. So what's different here? And I think at SimScale, we take a lot of pride in the methods we've been developing for, CAD preprocessing, mesh generation, solving, and whatnot. And so we take a lot of pride in those, but at the core, they are all about making simulation truly accessible, because we believe there's a lot of value to be created by using simulation earlier in the design process, broader, by introducing it into organizations that have not been using it so far. All right, and so for that, the way we do that is we like to say that we started from scratch again to think, how should a simulation software stack look like, instead of how it looks like today. And the way we describe, or our point of view on how most of the simulation software usages look like today, it somehow looks like this. You typically have a on-premise hardware stack, some high-performance computing infrastructure locally, some middleware on top of it, different software tools with different physics, and different vendors supporting that. And that stack is, to begin with, fairly expensive to roll out, fairly expensive to actually start, investing into something like this. Then it's time intense to maintain. And lastly, the software packages on top of it are oftentimes hard to use. And as a result, you typically only use it in the latest stages of a design process when you have mature designs that you want to validate by experts before you move to the production or before you go manufacturing them. And so the consequence of that is that simulation is just used very late, and in the other use cases where simulation could be useful, such as informing the design process in earlier stages, right? Some people call it iterative design or call it simulation-driven design, meaning that you don't wait for the validation stage, but an earlier one is something that is typically practically not feasible to use simulation there with such a stack. And beyond that, there's more, more even earlier usage, such as design space exploration, where the human is taken out of the loop and you automatically optimize a design, or on the far right, we can see the digital twin. So simulation use cases in support of operations for operational efficiency or for, predictive maintenance, these types of things. It's very hard to do that with this traditional on-premise simulation software stack. And so that was our starting point. We said at SimScale, how can we architect a new way to deliver simulation that makes simulation feasible for all of these use cases and also for all organizations, not just the largest ones that have already simulation capacity in-house? And it starts with, we believe the infrastructure, the computing infrastructure, in the long run will be a non-differentiating factor among engineering organizations, meaning that engineering organizations will start more and more to have the IT infrastructure outside of the organization. And so that was our starting point. We built SimScale cloud native, so really having all its compute power completely in the cloud, zero software, zero hardware footprint on the customer side. Then we integrated a set of best-in-class simulation technologies, starting from CAD, CAD preprocessing, meshing, simulation. We coupled them together to deliver end-to-end physics. And there's a whole host of analysis types for structural analysis in SimScale. Then we have separate thermal analysis types, and then a lot of fluid dynamics analysis, and those partially coupled. And all of these analysis types are available via a single web application. This application we'll see in a second anyways in action, so I'll not talk too much about it. So that means the entire breadth of these physics becomes available via a single web browser, right, to anyone in the organization. It doesn't stop there. We deliver all of this programmatically as well. So you have a web API where you can programmatically run physics simulations, be it, you want to automate simulation processes or customize them. And that is oftentimes then coupled with third-party or partner applications for those use cases. That's sort of, this is arguably the most complex slide of this deck, so the rest will be easier. But I think it depicts well how we think differently how a modern simulation software stack should look like in order to support all the simulation use cases and not just the design validation use case. So that's the area that we're going to focus on in today's session, because we cannot talk about programmatic simulation. We cannot talk about all of those good analysis types or these technologies. We're really going to focus on how SimScale is being used for design validation and iterative design, and how you can get started with those use cases. Now, before I go into the demo, so we'll have another 1 minute of slides, and then we'll do some live action here. Before I go into the demo, I think it's important to stress the fact what's different about what we're going to see in that demo in a second. And the way we like to explain this a bit is on the right, you can see a small diagram that shows the product lifecycle stages at the bottom and the performance and the cost of a product being developed on the y-axis. And sort of a mental model we like to explain and we like to work with our customers through is that if you think about how the performance and the cost of a product is being realized, it kind of looks like this. Right? And it's intuitive to most of the people, and everyone understands that in the concept phase it's easy. A few people conceptualizing a product, that's not expensive. It gets expensive the moment you start sourcing a supply chain, and then once you go into manufacturing, it gets really expensive. This is where cost is being occurs. The interesting thing about this graph is when you think about when product performance or cost of that product is being defined. And that curve looks almost like this. It's almost the inverse or a mirrored version of this. And if you think about it, the most important, the most instrumental decisions in a product design process are being made in the earliest stages. And now if you think about how most engineering organizations staff their tools and people against this, it kind of looks like this. You have initially designers, engineers, project managers driving the design, driving the hardware development project. And at some point, once you have a fairly mature design, you bring in the simulation experts, for reasons we already discussed, fairly late. They give specific answers to specific questions. Those answers are being used to finalize the design. As a result, simulation usage comes in at a stage where most of the product is anyways already defined. Right? And that is a big reason why a lot of the value simulation could create isn't created in today's engineering organization, or in most of them. And again, if we think about the concept we heard earlier, in this context, this is how we envision, or this is how SimScale is being used today by our customers. As a platform as a simulation platform that makes simulation accessible to everyone in the engineering organization, be it designers, engineers, but also simulation experts, and then they can collaborate on that same platform. As a result, you see simulation being used earlier, broader in the organization, and as a result, you end up building a better product faster. Now, lastly, just to wrap this up, in order to facilitate such a use of simulation, a simulation application must support work anywhere, anytime. Because if we've seen an organization that struggle with, somehow VPN deployed software on some workstation that sits somewhere, it's not going to facilitate a broad use of simulation. It needs to work anywhere, anytime. If that given simulation application has a steep learning curve, it's not going to see adoption, because if a designer or an engineer needs simulation every 2 or 3 weeks, he or she isn't ready to put a lot of training in. Collaboration is key. We just heard it. You need to bring the simulation experts and designers and engineers on the same platform to have that knowledge transfer, to validate certain simulations, to decentralize simulation use, but keeping quality control central. And then lastly, that's almost like table stakes. If your simulation tool doesn't solve the engineering issue at hand, you don't need to start. So it needs to be capable and robust in its ability to solve physics. All right, that was now 10 minutes of theory, so I think it's time for some practice action. And what I will do is we're going to talk about 3 different applications. We're going to look at a rotating machinery simulation, a thermal management application, as well as a structural analysis. We can see here a nonlinear Snapset. The reason why we've chosen these 3 examples is that what I want to convey is that this is not a one-trick pony where for a certain application works. No, it's supposed to deliver a broad range of physics to a whole host of engineering issues you face on a daily basis. We're going to start with the first one, with the rotating machinery application that we're going to look at in more detail. This webinar shouldn't be a training, so we'll not make this a training, but we'll take a closer look at the at this application, and we're going to take a more detailed look at this one. The other ones we'll just briefly touch to give you a look and feel. Okay, now let's quickly recap anywhere, anytime. Right, that's what we said earlier. And so the way I like to show anywhere, anytime is we start a simulation on SimScale by going into any web browser on any internet-connected device, and we type into the URL simulation.new. That's a domain we bought at SimScale at some point. I think it's a nice little gimmick because simulation.new brings you to the project creation dialog of SimScale. And I can type in, I want to simulate my centrifugal pump. The model, SimScale works with any CAD tool that's out there. So you can bring in from cloud CAD tools, the geometry. In this case, I'm bringing one in from a local CAD software. In this case, it was designed in SolidWorks. So I'm bringing in a geometry model, and that's being imported now at the moment. The anywhere, anytime means that we just, I'm on a standard laptop. I have no special hardware, no special software here. This is what you can see me sharing here is a Google Chrome. So it's a standard browser, and at any computer, at any device within your organization, engineers can access simulation thanks to the cloud nativeness of this platform. Right? And that's what we mean. Only that way people will really start using it. People will start using it broader, etc. If it sits somewhere on some workstation, it's going to be prohibitive for people to adopt it. Now, for the next, we're going to set up that simulation for the next 3 to 4 minutes. I want to encourage you to really stress, take note on easy to learn and easy to use, because I believe what we're going to show now after our CAD model is now imported, the simulation setup of such a centrifugal pump simulation isn't, that's not rocket science, and you're going to see it over the next 2 minutes. I encourage you to take a closer look if you want to try this out yourself. So here's the pump, a centrifugal pump for water. We bring in, water down here with a certain RPM for the impeller. Let's hide the rotating zone. And we have high pressure, we have a certain head over that pump. And the typical design scenario here would be for a given impeller and a volute shape, what's the head I can produce given a flow rate and a rotating speed of that impeller. And so what we're going to do is we're going to start creating a simulation. You can see you have access to all types of physics on SimScale. Unfortunately, we don't have time to cover them all today, but we're going to choose a certain a CFD analysis type. Let's give this a meaningful name. Operating point 1, CFD. We choose water as our material. We choose the velocity outlet as a volume flow. And for that pump, it is about 0.06 cubic meters per second. We have at the inlet, we basically say it's a pressure inlet, and we basically say gauge pressure 0, so that's fine. We just have a reference pressure of 0 pascals over here. And then lastly, we define a rotating zone, because we've defined here's our water going out at a certain with a certain volume flow. Here it's coming in. And lastly, what we need is the impeller to rotate. And so in this case, you can see the axis, the rotation axis down here. So I'll flip that around. And then, the good old right-hand engineering rule, we want to rotate the impeller in that direction. And we're going to assign it to the rotating zone. So you can see the impeller will now rotate in that direction, and thereby increase the pressure in the fluid that's going through. The last step we want to do is we want to use some result control items. That means what I'm ultimately interested in is the pressure increase over the pump. And so what I put in is outlet average. And so that's going to give me the pressure at the outlet automatically without me needing to do any post-processing. Lastly, I'll hit start. And my simulation is carried out in the cloud. Now, a quick recap. I brought in a SolidWorks model. I assigned, I chose an analysis type from, all the physics SimScale covers. I assigned a material. I defined the volume flux at the outlet, gauge pressure at the inlet. I defined the rotating region to rotate at the RPMs, where my pump is designed for. And I started the simulation. So this isn't something, that I guess is prohibitive or is hard to start to use. Of course, the devil is in the details, right? As this now becomes transonic or supersonic and whatnot, there's complexities that can enter such a simulation. In those situations, our answer is collaboration, right? If I'm not sure how to model something in a desktop deployed software, you would now need to go back and file a support ticket somewhere and maybe, dial somewhere. Because this is in the cloud, I can start sharing this project with others. I can start sharing it within people in my organization. For example, my colleague Valerio, I can share it with him, and he gets an invite, or I can also share it with the SimScale support down here. So you can see here's an integrated support chat. And so that allows me to share this project with someone, with the SimScale support team, and send them a message over here. I would have a question. That means everything, even the largest simulation projects on SimScale, because everything runs in the cloud, everything can be shared instantly with other colleagues within my organization, be it for support purposes, be it that I want to discuss results with them, or with the SimScale support team to have real-time support. Because now engineers can enter this specific project, we would see their head popping up here, and we would be in real time working with each other. Now, This simulation, this is a very fast solver. The simulation is going to take 3 to 4 minutes. So I'll, we could also wait, but I think we have better things to do. So I'll quickly hop over and go down here, and we'll just open up the prepared results just to go full circle and to give you an impression of also how result handling on SimScale looks like. And also, just to take notice, I basically open up a new browser window, just a new tab. So I have now 2 simulation projects open, both of which, on a local desktop system could contain quite some memory. I probably would have a hard time handling both of these models and simulation projects on my computer simultaneously. Because we're in the cloud, none of this is an issue anymore. Okay. Again, we don't want to make this a training. We don't want to get into too much detail, but just that you're sort of getting a feeling for what this now did. So this simulation, we can see this ran, I said 4 minutes, right? So it took 4 minutes to complete. And what I'm looking at here is the pressure field. So, as I would have expected, pressure increases over the impeller and going into the volute. Let's quickly turn off now I can start post-processing this and start understanding my design. I'll quickly hide that, and I'll want to cut the model. It's nice. Let's really cut it. I'm now looking at a cross-section plot, and I'm looking at velocity, and I can start visualizing the velocity field. And again, as expected, right, that checks out. The velocity within the water is increasing with increasing radius of the impeller, and all that good stuff. We could now show vector visualization, streamlines, etc. But I think, again, we're not here to now learn post-processing and SimScale. I just wanted to make sure that you understand really A to Z, right? That it's not just another canned demo, but that you're getting a feeling for the software that hopefully encourages you to try this out yourself, right? Good. I was hoping our simulation over here is already done. Yeah. So just as a proof point, you can see here that the simulation here would be ready. So I could now visualize this and post-process this over here. But that's not we've already done that. We've seen the post-processing of that simulation, and I wanted to spend the rest of the time to quickly take a look at 2 different physics. Because what we've seen, again, as a recap, is we just ran a analysis of a centrifugal pump in a browser application that is accessible anywhere, anytime. Hopefully, you got the impression that you would be easy. It would be fairly simple to learn this. We've touched a bit on collaboration. And so the next 2 simulations I want to show you hopefully convey a bit this element of that it's not a one-trick pony, but that it has a fairly broad range of physics and is robustly in its use. And so we'll quickly open up this one. This is a thermal management application where we can see this is a server rack with a bunch of electronics components in there, actively cooled. I have a fan up here. That's also one of the typical applications we see a lot in SimScale because it's so omnipresent, right? There's thermal management everywhere, chips are being put everywhere, and all of those bring thermal issues with it. The reason why I wanted to show this one is that this is a fairly heavy simulation. So it's a CHD analysis. So we have convection, conduction, and radiation coupled within the same simulation. So it's a true multiphysics run. And thanks to the cloud, this has, I think, 11 million cells, something like that. So it's a fairly heavy mesh. And it is, it's still able to run all of this in a browser, thanks to all the computing power that's available in the cloud. We can then animate this. And again, I think like the physics here makes sense, right? We have a fan inlet over here, and we have a heated component over there. And we're bringing in the active air cooling, and we can see the temperature fields over here. White is very hot, and dark orange is colder. And so we can now see whether or not our components operate safely. And now, Linda told me earlier I shouldn't go over 25 minutes, so we literally have probably 60 seconds left. So I'll quickly just hop over to the last example where we're looking at something very different, a structural analysis, in this case, a nonlinear Snapset analysis. And in this case, you can see we're bringing in a snap fit closing into an enclosure, and we can design now those snap fits and make sure they're not breaking when those things are mounted. All right, with this, I'm wrapping this up. I would really encourage you, it was just 25 minutes, so we didn't have a lot of time, but thankfully for all of those applications, we have tutorials available. And so you will be able to access this PDF that we provided as a PDF, so you can click on those links, and you can just create a free account and try them out yourself. With that, Linda, I'm wrapping up here. Thank you so much.
Okay. Thank you, David. We do have some time to take some questions from our audience. The first question is, which CAD files do you support, and can those be edited in SimScale?
So to the second part of the question, yes, SimScale has a pre-processing environment, so you can do CAD editing in SimScale, such as flow volume extraction, simplification, contact detection, imprinting, etc. So it's not meant to author CAD, but it's meant to prepare CAD for simulation. On the first part, which CAD models we support or which CAD formats, I guess it's fair to say that among our user base, we probably have any CAD system that's around. We have them all. Many of them, most or probably all the big ones, we support natively. So you can bring in native CATIA files, native SolidWorks files, native Autodesk Inventor files, etc. For the ones we do not support natively, we have all the general exchange formats, STEP, IGES, STL, etc.
Okay, so that kind of ties into the next question. What type of cloud backends or cloud partners are supported?
SimScale runs on AWS, so the Amazon cloud, where we do make full use of all of the infrastructures. We have GPU solvers in SimScale, CPU solvers, etc., and we're always tuning the ideal machine for the simulation job at hand.
Mm-hmm. So you actually alluded to this. 3 minutes for a centrifugal pump CFD is very fast. I guess without giving away any trade secrets, how do you solve CFD so fast?
I mean, as I said earlier, the devil is in the details, right? I mean, this was really this was an early stage, quick, rough analysis, right? So of course you can dial up the cell count and make it more make it a more higher fidelity simulation, and then also the runtime increases. And so that's why we need to take a closer look at how this was modeled. But I think it's a fair point, because specifically for rotating equipment, SimScale at its back end runs many different solvers, each tuned for the specific application at hand. And for our the rotating machinery application, we use a solver by our partner company Simerics. They have a fantastic finite volume solver, a fantastic, incredibly fast solver that allows those very fast runtimes.
What kind of support and collaboration features does SimScale have?
I probably should have demoed them better earlier, but if anyone has already used, for example, a Google Doc or a Microsoft 365, Word online document, one is used to this really real-time collaboration on a document. And this is what we've built at SimScale for simulation. So you can in real time access the same simulation project with your colleague. Both can, edit it. And the same goes for our support. So oftentimes our support engineers work very close with our customers, because they can just effortlessly, seamlessly work on and collaborate on their simulation project. So it's hard to explain. So I'd really encourage you to just sign up for a free trial, give it a spin yourself, try out the support. It's I think it's something new in the engineering software world for sure.
And what applications can you simulate in SimScale?
Yeah, that's a hard to answer in a few seconds. But I think I'm still sharing my slides. So I'll quickly hop above. So these are some of the applications. You can see the range, right, from static stress analysis, stress and deformation, over vibration analysis, sealing, crushing, you name it. So a whole range of structural analysis, over to thermal. We do a lot of work in electronics cooling, but also heat exchangers. A lot of customers And then over into CFD, we've seen a rotating equipment example, but so is, external aero, process engineering, multi-phase flow. So it's hard to answer in a concise way.
What is pricing based on? Is it based on simulation physics, model size, processor time?
Nope, it's a fairly simple way. It's an annual subscription, and you get access to full physics, and and then you're off to the races essentially.
Okay. Looks like that's all the time we have questions for today. All the time we have for questions today. I would like to thank our speaker and all of our audience mending. Just a reminder that this webcast will be available on demand for 12 months at www.techbriefs.com. Thanks again and have a great day.
Thanks as well, Linda. Bye-bye.